Do we start?
Yes, whenever you are ready.
Okay. Salut Alan. Hi Misha. So now we can listen to the second talk of Lucy, please.
Okay, so I will continue with the theorem that I stated at the end of yesterday's talk about an example where you get infinitely many inequivalent real forms of a relatively simple, rational, four-dimensional, affine variety. It's given by this one. And the sketch of the proof, I will just give you the ideas behind the proof, because what I want you to remember about the idea is, one, I'm not claiming to get all real structures or real forms of this variety. I'm just getting an infinite number of them. They're countably many, but I'm not saying they're all of them. I'm just going to give you some of them. And also that the way that I will construct them is using vector bundles. Okay? This is kind of the thing that makes the theory work. There are several places where calculations have to be made which are not difficult but are a little long, so I won't do them. But I'll give you the idea behind how to do this proof. So the idea will be the real forms will be of the real forms will be rank 2 real vector bundles over the real sphere. So I'm going to construct such objects such that when you complexify, they become rank 2 vector bundles over this sphere that are trivial. Okay? So, okay, that's the idea, but now I'm going to turn around and go the other way. I'm going to start with a construction of rank 2 complex vector fields over S2C, and then define real structures on them that give these real forms. So the idea is as follows. I'm going to, just for simplification or I'll remember that this variety is isomorphic to what I called HC yesterday. It's the spectrum of CUVZ such that UV plus Z squared minus 1 is 0. Okay. Why do I want to write it in this way? I mean, this is, of course, it's the same as saying x squared plus y squared plus z squared equals 1 over the complex, because u is, I'm thinking of u as x plus iy and v as x minus iy. Right? And that's giving me the sphere. But this is a nice way of writing it, because this HC is a surface in C3, which we call, it's a very special surface. It's what's called a Danielewski surface. It's a surface which was studied very, well, it's still now being studied for the problem, the cancellation problem. There's an open problem in algebraic geometry that if you take X, a affine variety, and you say X cross C, and you say this is affine space, is X also affine space? And this is not known, but with Danielewski surface, things like of this form, it was shown that X and Y can be non-isomorphic, but X, the cylinders X cross C and Y cross C become isomorphic. And these were done by surfaces of this type. They come up very often in many results about affine algebraic geometry because of this property. So I just want to say a little bit about this nice variety. You take HC, you can just project it down to C just by saying UV. See, I'm going to project it to U. Now, if I do that, you see that when U is not 0, the fiber is just a copy of C, because V is just Z squared minus 1 over 2. And when U equals 0, I get the fiber being 2 copies of C. So I've got 2 copies of C. So what you can see from this is quite easily that the Picard group of HC is just Z, generated by a divisor. I'm going to call it du, which is given by u equals z minus 1 equals 0. Okay. If I say u and z minus 1 equals 0, then v is anything, and that gives me one of the fibers. So this is, in this fiber, all of the fibers are, what this is, it's a locally trivial fiber bundle over C with a double point in the origin. Okay. On the origin, I have 2 copies, and so that's why I have this Picard group being Z, and I can describe the Picard group. And if I say dV equals V, Z minus 1 equals 0, then du is equivalent to minus dV. Okay, so what I'm going to do is start by constructing a rank 2 complex vector bundle on HC. Okay, and it will be simply O n du plus O minus n du over hn. This I will call Wn. It's the sum of 2 line bundles. Okay. 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 So here's my rank 2 vector bundle, and I can well, first claim is Wn is isomorphic to a trivial bundle. AC to HC, sorry. Now, this is, one could prove it directly, but you...
Which is HC.
HC, the base, cross...
Just the line just before.
This is... No? C, yes. Yeah. Ah, yes. Oh, yes. That's right. I see. Right. Thank you. Okay. So one of the ways to see this is by this result of Murdy. Is he said that over HC, which is the same thing as a complex sphere, any rank 2 vector bundle can be factored. Wn can be factored into O plus some other line bundle. But if I look at the determinant is 0, so this line bundle is trivial. Okay. So that is a trivial bundle. So this Wn, that's the total space, is just S2 cross AC2. But I will use it to construct a real structure that is twisted by these things. So the way I'll do this is I will look at the base, HC, HC. I will define I wanted to call it mu, I think. That's right, mu, which will be a real structure. Which sends u, v Z to V bar, U bar, Z bar, in such a way that the fixed points on the base will be the sphere, the real sphere, topological real sphere. And here, I take this Wn, I go pi, and if I look at the pullback diagram, what I'm going to get is a copy of Wn here, and a real structure on Wn. It's just constructed by looking at what happens to U and V when I do this, and I look at these functions on the base. So that gives me mu n is a real structure on Wn. Now I claim that all of these therefore give me real structures on this variety, and I claim that they're all different. And they're all different because the fixed point set are all non-diffeomorphic 2 by 2. So I'm just going to make another claim. Okay, I'm going to look at the topological setting. I look at fixed point sets. If I look at the fixed point set on the base, I get the real sphere. That's why I switched to U and V. And on the top, I'm going to get a rank 2 vector bundle, which I will call En. And, well, I'm not going to do it here, but it's not hard to just look at the transition function and find out who this is. Well, we know about rank 2 vector bundles on the sphere. They're given by Z. So for each then, S2 is 2 disks, disk U1 or North Pole and the South, and then on the equator there's a clutch function, or you just transition function, and on the transition function it's given by rotation, a winding number. And I just take this, I check who the transition function is, I look what it does to the fixed point set, and it just rotates within the winding number n. Okay? So that means that these
En
is the total space.
Rank 2 vector bundle.
This is a rank 2 real vector bundle on the real sphere on on S2. Well, so I shouldn't put R here. I should S2. The real sphere, a sphere topological. Okay, so it's just a 4-dimensional real topological object, and so I make this calculation and I find out that this is En. Okay, now I claim that En is diffeomorphic to Em if and only if n is plus or minus m. Now, if I have that, I'm finished, because that means that I have, for n positive, I have an infinite number of different real structures that give me objects whose are all topologically different. Now, if n equals minus m, it's pretty easy to see that they are the same. And well, there's several ways of proving that if n is different from m, then the topological spaces are different. I'm going to do it because I like it that way, of using, of describing it using complex line models. Okay. Okay. So yes.
Can you say again? I didn't get why, if you have this one, why
We're finished.
Yes.
Because I have, for each n, I have a real structure on the variety, and its fixed point sets are going to be these objects. And if the fixed point sets are not diffeomorphic, that means that the original real structures are different. Okay? So if they're never diffeomorphic, so that means for n equal 1, etc., 2, etc., I'm going to get a different one. For 0, I get a trivial one. For 2, I get the tangent bundle of the sphere. And I say that they're all topologically different. And one way to see that is looking at P1C is diffeomorphic to the sphere. And a way to construct En is by looking at the line bundle On over P1C. This is a complex line bundle. But if I just look at it as a real topological vector bundle, this is the sphere, and that's On. En is On. Total space of a line bundle, a complex line bundle. That again, you could just calculate the transition function, and you find this. This is not hard to do. Now, why do I want to do that? Because, well, I'm just going to go back to the first lecture that we saw of Carolina, that she said on P1. See, I'll do it here. P1C. I can put over here On plus O projective. This is a Hirzebruch surface. Fn projective surface. And what I have is this En then is an open set in Fn that gets completed by the Fn minus En is one section of self-intersection minus n. And what one can do in that case is calculate the first homology group at infinity of this total space. And because of this self-intersection, it's Z over NZ. Okay. So if I have n not equal to plus or minus m, the first homology group at infinity are different, so they're topologically not equivalent. Okay? So that finishes the proof. Okay? Again, I'm not doing the calculations, I'm saying how you can do that.
So what is the conjugacy between O of n and O of minus n in the...
Well, they're on different objects. This O on n is on P1. Mm-hmm. It's just 1 point. It has a divisor that's 0 on 1 point. And the On, well, the other On that I had, Wn, so well, it was NDU. It has other objects there that give me, this N just gives me the winding number. Mm-hmm. Okay? But this N comes from it, okay? So that means that all of these ENs, so it means that the fixed point sets of these objects are all different. And so I have found, that means that, yes?
What is H infinity 1?
It's the first homology group at infinity, okay? You look, you complete it and you look large enough at infinity, what happens to the, okay? So that's one invariant that you can use to distinguish these objects. Okay, so this finishes the sketch of the proof, let's call it. And I just wanted to make some comments that actually, what?
Just one remark. For those
Yes.
who doesn't know what's the homology at infinity, they can also take out the zero section, right?
Yes.
Just look at the homology.
Yes.
Complement toxicity.
Yes. It's just to say that if you take Fn and you take out the section at infinity, and you take Fm and take out the section at infinity, they're not diffeomorphic. That's what I want. And this is one invariant that makes a difference. There are many others. But, so I just wanted to make some comments about history of this problem. Well, first of all, Barge and Oyon-Buren in 1987 proved, well, more generally, but among other things, two algebraic real vector bundles on S2 are isomorphic if and only if the real points are diffeomorphic. Well, one direction is clear, is if they're isomorphic, then these are diffeomorphic. So I have things that are non-diffeomorphic, so I know that the vector bundles are not isomorphic. But what this is telling me that using this method, I have all the real structures on S2 cross A1 that can be given in such a way to keep a vector bundle structure. Maybe they're ones that break the vector bundle structure, that could be. But if I want to keep the vector bundle structure, I've got them all. Well, okay, so I think I am going to, there's much more that can be said about this example, but I think I'll stop here for the example of infinitely many real structures or real forms on a variety. And I'll start the second part of this talk, which will be based on the real structures in the equivariant setting. Real forms and structures in the equivariant. So in this case, we take G will be algebraic reductive connected complex group. If you're not familiar with reductive, doesn't matter. You can just think of C star or C star to the power n, SL2. Those are the ones that I'm going to be most interested in, but of course you can do SLN, there are many others, okay? And what I'm going to consider now X will be a G variety. And I want to define a notion of real form of everything. That means real forms of X which are compatible with real forms of G. Okay? So I will start by defining the object. First, what is a real structure or a real form on G? This is very well known, and I'll start with real structure on G. What is that? It's just the same thing as a real structure on X, only I want the involution to be a group homomorphism. So I'm going to say sigma is a real structure. It's of the form sigma, where I have G, sigma, G, over spec C, spec C. C goes to Z bar, and sigma should be an anti-regular group involution. It has to preserve the structure of the group. Now, real structures on reductive groups is very ancient history, right? We know, for example, SL2 has up to equivalence 2 real structures. Where the fixed point sets will be either SL2R or SU2. C star also has 2 real structures, where the fixed point sets are either R star or a circle. Okay, so these are the kind of things that I'm going to be talking about. Okay, so I have a real structure here, and of course I also have the equivalence as before. Sigma is equivalent to sigma prime if there exists phi, a group homomorphism of G such that phi sigma phi inverse equals sigma prime. And then, so we can define a real form on G is a real group F such that F spec C over spec R is isomorphic to G as a group. And as before, real structures are in bijection with real forms. And I can calculate up to equivalence all the real forms by looking at a first cohomology of gamma with these automorphisms of C on G, just as we did before, only these groups are group homomorphisms, and gamma is, as before, Galois C over R. Okay. So now I know what a real structure on a reductive group is. And now I will say what it means for X to have a real structure compatible with X. I'm going to give an example in a moment, but I just wanted to start with the real structure on a G variety. Okay. Okay. If X is a G variety and sigma is a real form, real structure on X, then a G sigma form or structure on X will be just mu from X to X, a real structure. But such that it satisfies a compatibility condition here that's just mu of Gx will be sigma G mu X for all X in X and G in G. So it's not equivariant, it's equivariant and twisted by this structure here. So let me give some examples. Let's start just with examples of okay.
G variety means that you have an action of
What?
G on X.
What?
The definition of G variety.
G variety, it means it has an action of G. So G is complex, this is complex, and it has a complex G action. Okay. Okay. G variety means it has a.
Do you assume it's faithful?
No, I don't ask for it to be faithful. Any action. Right. Okay, so just some examples. I'll start with the group C star. Okay, like I said, it has two real structures up to equivalence. There's sigma of G equals G bar, and there's sigma of G equals G bar inverse. Okay. If I look at the fixed point sets, here I get R star, and here I get a circle. So it's easy to see that they're different. It's also very easy to check that every real structure on C star is one of these. But I wanted to say this because now I can look at C star not as a group, but as a homogeneous space for C star. I don't call it a group, I call it now just a variety that has an action of C star. And I can say, oh, okay, I'm going to look at these two different real structures on the group and say, well, do I have real structures on this C star variety that are compatible with this one? Well, I can, for mu, well, it's obvious that I can do this. That works just fine. Mu 0 is a C star sigma 0 structure. I could also do mu1 G, which is the same thing, but just, okay? And that's a, mu1 is a sigma 1 structure. But I can do something else. I can do mu2 of G is minus G bar inverse. And mu2 is also sigma 1, a C star, sigma 1 structure. I know these two are different because the fixed point sets are different. This still has no fixed points. Fixed point set is empty. Okay? So C star, as a homogeneous space of C star, has 3 different real structures. 1 compatible with this, 2 compatible with this. And, okay, so group and homogeneous space is not exactly the same thing. Okay. Okay, SL2, okay. Okay, so I will, well, there are many other examples too, but I will just say for SL2, okay, that was 2 structures, 2 real structures of SL2. There's sigma S of G equals G bar with fixed point set SL2 R and sigma C of G, which is G bar inverse transfers, where the fixed point set is S mu2. Compact, that's why I say C, semi-simple. So this is split, this is simply. All reductive groups have been done over years. One can find all the real structures, they're well known. Okay? And these are the only ones. For SLN in general, you get the SLPQ, SUPQ, and etc. So you have these different ones, and you can say, like, for example, if I look at P1 as a SL2 variety, then it has one form, one structure for compatible with sigma S and one compatible with sigma C. But there aren't 2 that are compatible for the same varieties. Okay. Okay. So let me just say what we can now do with this theory. So the main question in this theory is given X a G variety, and sigma a real structure on G, find all equivalence classes of G sigma structures. On X. This will give us much information about the action of G on X compared to an action of the real points on the real set. Okay? And so, well, let me just look at one example that I will be interested in. Okay. An example that generalizes the cases that I put here. I put C star there. I put P1. I'm going to suppose that X is a homogeneous space. And sigma is a real structure. And I want to first say, does a real structure exist on X, which is compatible with sigma? And I can tell you the answer and even prove it. X has a sigma, G sigma, compatible real form, real structure. If and only if there exists, let's be careful, a K in G such that sigma H is conjugate to H and conjugate by K. And sigma K belongs to H. It's a cohomology condition again that I'm writing down here. Okay? But I will show you why. Okay? Okay. Okay. Proof of this little result here. Okay. If I want to find a real structure on X, let's call it mu of H is going to be some element, which I'll call KH. But first of all, I need that mu of H has to be the same as mu of H, which is KH. And this is sigma H, KH. This means that K inverse sigma H, K belongs to H for all H in H. That's my first condition. Oh, did I put it the wrong way around? Okay, I'll do it K minus 1 here to make it right there. Okay. Oh, no, I did it right before. It was right before because it was the other way around. This means that sigma H has to be KH, K minus 1. That gives me my first condition. And also, I want that mu of H, mu of H has to be H. This means mu of KH, which is sigma K, KH has to equal H. That gives me the second condition. So for homogeneous spaces, it's very easy to find the cycles, find the forms, and then I have to say when they're equivalent, etc. But to find the forms are quite easy. And so, okay, I think I won't do this one, and I will Yeah, because I'm running low on time. Okay. So these cases of homogeneous spaces are not hard to, well, they are hard, well, they're not easy, but they can be treated in a relatively simple way, by just checking if you have these two conditions. And then finding the equivalence is not much more difficult than that. In my lecture, on my final lecture, I will be giving examples of that, of what happens for homogeneous spaces, and then I'm going to continue a little and say almost homogeneous space. An almost homogeneous space is a space where there's an open orbit that's homogeneous, and then there's some other orbits. But that's for Thursday, right? So what I want to do today is just say, come back to the vector bundles and just spend, well, yeah, I have, what, 7 minutes? 7 minutes, okay, 7 minutes. I'm going to do something else today, is that I can look at the example of C star acts on C4 linearly, okay? Where, okay, with a linear action, okay, I'm going to do with a linear action. C4 will have weights 2, minus 2, n, and minus n, where n is at least 5 and n is odd. So can't be nicer, nice little linear action. And I'm going to use the sigma of t equals t bar inverse is a real structure. On C star. The fixed point set is a circle. T equals t bar inverse, that means t is of norm 1. Okay? And I want to tell you the result. In this situation, okay, result, okay, theorem. There exist uncountably many C star sigma structures on C4 with these weights. Okay. Now, the reason I want to tell you about this result is because it's very related to the first result I did. What one does to find this thing is one uses vector bundles. In this structure, I'm looking at C2, C4 as a trivial vector bundle. A trivial vector bundle if I forget the action. Okay. It's just a vector bundle over C2 with fibers here. And I put weights of this action here. And what one can do is, in the very similar way than from what I did before, construct real structures that make the, well, I'll say it like this, because time is running out. Comes from an old question of find non-trivial G vector bundles over a G module. Kraft and Schwartz in the 1980s found many examples of reductive groups where on the bottom you have a G module, on the fiber you have a vector bundle. The total space is a G vector bundle, but it's a non-trivial G vector bundle, equivariant G vector bundle. Okay? G acts on the base and on the space, and G acts linearly on the fibers. G equivariant.
You wrote G module instead of G manifold, right?
No, the base is a G module. B is a G module. E over B. So it's a G vector bundle over a G module. The base is a G module. So for me here, the base is the C star with base 2 minus 2. And E is a vector bundle over it. Okay? This is a trivial one, right? This is a trivial one. But what they did is they found non-trivial G vector bundles, for example, for G being O2, which is C star cross Z2. They were interested in this because if you take away the group action, E is just affine space. It's just a vector bundle over affine space. So it's just an affine space. But the action is strange. So they were interested in this to find non-linearizable action on affine space. And among other things, they found these examples. This has an action of C star and an action of Z2. And that's just what I want here, because I have C star acting. And what is a real structure? It's an involution. So one can take this action that they have here, twist it, make it complex, make it real and complex, and find uncountably many real structures on C4 using this vector bundle structure. I'll just close by saying the ideas behind this look similar to what I did in the beginning. So the theme of the day is vector bundles. But there's a big difference. In the first examples, I distinguished the vector bundles by topological invariance. These, topologically, they're completely trivial. It's a very algebraic phenomenon that happens here that makes them different. So I think I will stop there with this example. So the idea for Thursday will be to come back to the case of homogeneous spaces and then make them almost homogeneous and see what we can do in that case for this setting. Okay. And that's...
Thank you.
Okay.
Are there any questions?
Tried to say too much. Yes. Okay.
please.
So when you say that they are topologically trivial, these different G sigma structures on this last example,
Right.
do you mean that you understand the topology of all the actions and they are all the same foliation by circles, essentially topologically conjugated?
You just look at the real points, they're all completely trivial. They're just foliation, they're just a trivial vector bundle, topologically.
But
They're all-
and the foliation, it's also,
Okay,
do they
so-
change?
Okay, let's see what that means.
Foliation is by the orbits of the real action. I mean, it's a foliation by circle, right? With
Yes.
some singularities,
Right,
points.
okay. On the real
Besides that,
action,
you have a bunch of circles.
I think that I would, yeah, okay, so they're just, it's a circle action on R4, and all the foliations, they're completely, yes, they're diffeomorphic with the circle action, so all the foliations, all the orbits of the circles are diffeomorphic. The reason that they're different is algebraic.
Thank you.
Okay, if you consider the toric varieties,
Yes,
then on C star you have what you call the sigma 0 and sigma 1.
yes.
So do you have some structure compatible with sigma 0?
Yes, they're ones,
Sigma
well,
1,
well, for this example, you can do ones with sigma 0, but they don't give me anything interesting. But
But they are.
But there are. But what I will be talking about the next time is like toric varieties. You're going to take C star to the power n. You look at what are the structures on C star to the power n, and you get copies of these two different sigmas plus another one. And then you can embed that into that's open in some almost homogeneous space. And the question is, does this almost homogeneous space have a structure? The difference here is that the orbits are a very high codimension. It's very hard to find everything. But if the orbits have high codimension, then one can hope to have more information.
Okay. So let us thank Lucy for the talk. So tomorrow we meet for talk, a short talk station.
Yes, it will be the big day. So starting at 10 a.m. here, and everybody here in Brazil, from the Brazil side, promise to not take longer than 30 minutes. Huh?
Okay.